Hello, everyone. Welcome to the third conference at the Data Track. Today we have with us Sergei and Natalia, two Ph.D. in mathematics. Sergei is an independent software engineer consultant, and Natalia is data scientist at Allianz, and they will be presenting for us Fullstack Data Scientist 2021. How much of software engineering should a modern data scientist know? So I give the word to you, Sergei and Natalia.
Thank you. So hi, hope you are doing well and enjoying this online PyCon Sweden 2021.
So my name is Natalia. I'm data scientist at Allianz.
And I'm Sergei. I'm an AI software engineering consultant currently at H&M. Today we will talk about what we call a full stack data scientist.
So I got my PhD degree in mathematics and spent a few years in research and education. A few years ago, I got interested in data science. I had a few assignments as a consultant, and recently I joined Allianz as employee.
I also have PhD in mathematics, but turned my career towards software engineering a while ago. My mathematical background defined my interest in data science, but from an engineering perspective. So now I'm an independent consultant, and currently I am at H&M.
Data science as a separate independent discipline is relatively fresh. For quite some time, it was a lot experimental. There was a lot of research, development of theoretical background, algorithms, and tools. One of run, what was it? Nowadays, it's different. Data science left research labs, and now it's used by different commercial companies, big and small. No longer it's just research. It's a tool that adding value to the company, and hence trade by the management as any other tools. Data science should bring value, and the business expect it running the same way as any other software, became a part of our software solutions and have a predictable release cycle. What's it? Business sees it as software, just with a little magic or math above, but developed, operated, and maintained like any other software.
And since it is software, it should be basically have the same quality as any other modern software. So it should be resilient, it should be scalable, it should be secure, and so on. So how do we reach those in our data science projects? So since data science works with data and is kind of software, we can say that modern commercialized applied data science is what we can call a full stack data science, comprising of data engineering, data science specific algorithms, and domain knowledge, since we're solving real business problems. And finally, software engineering, since it's supposed to be software. That diversity is usually solved by having a cross-functional team, having on board at least a product owner with deep domain knowledge or any other domain expert, data engineer, data scientist, and finally a software engineer in data science. But on the other hand, not every company can afford such a team, especially when they're just in the beginning of their data journey. And data scientists should talk to all the other people in the team and understand, they should understand the same language. The roles, as we see, they are like very common definitions, I think. So a data scientist is someone who is using all these data scientific approaches and algorithms, from statistics to machine learning, operational research, and so on, to get something unexpected from the data that is in. The data engineer is usually someone who does all the data preparation, maintains the data lake, other storage data solutions, ETLs, and the software engineer brings everything to life in production, right?
Yes, but all of them write code.
Exactly. That's why the border between those roles is not really well defined.
So I'll tell you one case from my own career. A few years ago, in the beginning of my career as a data science in commercial sector, I joined a fast-growing e-commerce company. We were two data scientists who worked without any support from software engineers. My first task was to do some research and analyze customer behavior. R seemed like the best tool for it, so I made a solution in RStudio. Next was to do some predictive analysis based on that research. I just continued with the R code. When stakeholder asked for some data visualization, I also did it with R, just extending my script, still running in RStudio on my laptop. When they asked me to build a PDF with all the tables and graphics, I managed to make R work with LaTeX. But the really challenge was next step. We wanted the analysis PDF to be mailed them every day and asked to deploy the solution to AWS Lambda in a moment. I had to learn what is cloud, what is AWS, what is AWS Lambda, how do I deploy my solution there. I had to learn Docker and manage to get R into LaTeX in the same container, and it didn't work in production.
So what does it mean? What should a data scientist do? In some sense, a bit of all of those things. So gathering our experiences in working both as data scientists and as software engineer in data science, and having worked both alone and in cross-functional teams, we tried to collect the things that a modern data scientist working in the commercial sector should know to effectively deliver scalable, production-ready solutions and work effectively together with engineers and data engineers. So since all of us more or less write code, let's start with programming languages.
So I started my data science journey with R. It was a great tool for doing statistical analysis combined with SQL for data preparation. But I switched to Python when I started doing machine learning. Still, there are a lot of cases where R has fantastic libraries for solving certain problems. When I joined a new team and started using databricks, I had to learn Scala since a lot of code was already written in Scala.
Yeah, exactly. You should always pick the right tool for a certain task and be flexible to learn new languages and mix a few languages in the same project, right?
Yes, I will also mention SQL. Oh. It's not a programming language, but we will most probably have to work with SQL data sources. It could be a Snowflake, Google BigQuery, or databricks. And it's important to prepare the input data the way you need.
Yeah, I cannot agree more. I also would like to add that shell scripting is also something that you should probably learn because it's such a simple way to automate so many things.
Here is my advice to junior data scientists without much programming experience. Always be learning your programming language and new features. You should not be limited to data frames and a few specific libraries. One day, you will have to write a data class or regular expressions.
I can completely relate to this. And from my perspective, you as a data scientist also should learn how to write clean code. Clean both in terms of architecture of this code and how basically it is formatted. Starting from all the, we are talking Python, obviously it's PEP 8 and all the best practices around these recommendations. This will make your code much more cleaner both for you when you return and you have to maintain this code and to your peers, right?
Yes.
So we talked about a bit about writing code, but let's get to production, because that's what is usually our goal, is to get things in production and start delivering some results there. So the way you run your code in production depends on the problem, on available execution environments, and on many other factors. So what are the most typical ways you are running your data scientific code in production nowadays? So we often start with Databricks notebooks. And actually, you can just use them directly in production. You can schedule a notebook in Databricks, and it will be executed on a schedule. That's the way to go. Many of other things you can actually transform to a separate Python executable and just run it in Kubernetes or on VM, just with a cron, if it's something that should be run on a daily basis. If you go in forward and speaking of more complicated things, including certain steps, that's usually what is called a pipeline, and usually is automated, orchestrated with kubeflow, airflow, or another alternatives. Speaking here, we really need to understand the differences between those runtime environments, and we will talk a bit about this later. But this is mostly some kind of bad jobs, but there are other cases, right? So imagine we're building a recommendation system for the customers visiting an e-commerce website. So each time they visit the page, we have to show them recommended products like bestsellers, upsellers, and such. So the request goes down through the rest of the architecture of the e-commerce platform and finally lands into your service. So it will probably land up with an HTTP request. So you have to deploy some kind of API. And most probably you will be deploying this on Kubernetes. Or in some cases, you might go serverless because there are so much great things like Google Cloud Function, AWS Lambda. So everything is definitely depending on the use case, and you are definitely free to mix and match. The only thing you need to know this platform and its specifics. So know your runtime environment. You need to know how does it work in general, what kind of a process isolation is there, how does it scale, how does it parallelize the things if it does, finally, how you can troubleshoot it. And for this, you need to know where the logs are, where the metrics are, how can you monitor the resource usage, and how can you manage the resource consumption. There is a typical use case when your Kubernetes pod just crashes because there is not enough memory. So you probably need to learn those specific Kubernetes things. How can you request more memory for your specific container? The same applies to any execution environment, is just different. So if you are talking about Spark, you also need to plan in advance how many nodes of the Spark cluster you really need, how big or small should be the nodes, and it's definitely not a trivial thing, but you need to learn their execution environment to really be able to use it to 100%.
I hope you run your data science code in the cloud. Major cloud providers like Google Cloud Platform and Microsoft Azure provide great tools from big data storage solution to pipeline orchestration. We are constantly adding new things. Look what your cloud provider already offers. Maybe you don't need to reinvent the wheel. It could be anything from hosted Jupyter notebooks to kubeflow pipelines to hyperparameter tuning.
All right, I have quite some not perfect experience with inventing the wheel. So this happens.
One of the modern engineering practice is splitting a big software project into smaller ones. It makes it easy to manage, deploy, and troubleshoot. So split your code into several models, make it easy to focus on certain part of works, and collaborate with peers. When possible, split a single long-running process into few steps. Save state after each step. You will be able to rerun only the fail parts. You can use kubeflow or airflow to automate this. You probably don't want to break production, especially corrupt data, and don't test in production. Create a develop or test environment that is isolated from production. On your laptop, create a dedicated virtual environment to each project, so you don't have problems with conflicting library versions.
Yeah, here I completely agree. And about the virtual environments, in case your execution platform, your production execution platform, doesn't provide any good environment isolation by default, like Docker does, for example, then you need to think how to manage virtual environments there as well. But now let's talk a bit about data. You need to get data in, you need to provide some results. So generally speaking, very simplified, we have two options. Either you get something from the storage or you get something from the API. And the same for the data out. Either you write something to some kind of storage or you return an API request. Let's start a bit with the storage, right? So in case you're doing big batch processing or model training based on historical data, you will probably access in the storage. Without diving too deep, we can simply say that there are database solutions like file-based solutions, though sometimes the border is not that well defined. So if you previously worked with relational databases, you need to understand what the columnar storages like Google BigQuery, Snowflake, and such are different from. The difference lies in the way the data is stored. So in the relational databases, everything is based on rows, while in the columnar data storages, it is based on columns. That's why certain operations have completely different costs. So, and there are no traditional indices in the columnar storage. They are very different. So certain operations could be extremely costly for columnar data storages. So certain types of joins, certain types of column, table updates and upserts, they could be completely different. So you need to rethink how you plan your query and how you read the query plan in an analyzer. Other than that, there are document databases. It's a completely different animal. If you have to work with them, you really need to dig deep into this. If you're working not with databases, you're probably working with files directly. Either they are located locally on a blob storage. Usually this is either a CSV or Parquet, if you're talking about some kind of like tabular data. There is a huge difference between CSV and Parquet. So CSV is a text file. It is row-based, and it doesn't have any schema or any data types. So you have to infer data types somehow from data. And in some sense, that's a very unstable and very undesirable file format, but it's still widely used because integration with upstream and downstream systems is very easily achievable with CSV. Everyone can read and write CSV, all the systems. So Parquet, in many cases, is much better than CSV. It has strict data types, so you can control the schema of your columns. You can enforce basically this schema and guarantee that the whole column has an expected data types. You can also do partitioning of your Parquet storage that later will benefit if you're reading a lot of data from it. There are definitely other file formats, but these are probably the two most common. You probably worked with local file system, but at some point in time, you will have to work with a cloud-based blob storage. In many runtime environments, the local file system is something ephemeral, it's short-lived, and you cannot use it as an exchange point with other systems. So you have to copy over the files to your blob storage. And all the major cloud providers, they are so different on those APIs. You need to learn not only how to use their SDK, but also to understand the differences in the behavior. Sometimes you cannot just overwrite the file. There is no such an operation. You have to create a new file with a different name. You cannot append the file and so on. So that makes you think completely different in the way of doing I/O operations. And finally, and first of all, understand your schema and understand your data type mapping, because the data types that are somewhere in the database could not map directly to the types you are using when you're reading the things. Because you could probably read the CSV with a built-in CSV reader, or you may be reading this directly to your data frame. And the results could be slightly different if you are using Pandas data frame and Spark data frame. They're just named the same way. They are very, very different. So these names should also not confuse you. A couple of words about APIs. We touched an example with the RESTful-ish API that provides the recommendations. So if you're about to deploy those things, it's not just enough to learn how to build these things with Flask or Sonic or Fast API. You really need to understand the network basics, what can happen on the network. You really need to understand what happens on the HTTP level. So the terminology of request and response, and the possible encodings of both the payload or request and your output, the response. So a very common thing here is JSON, and it has kind of the same drawbacks as CSV has. It has very limited types, it is schemaless, and so on. So lots of drawbacks, but it's so widely used, you have to learn how to deal with it. Modern companies with lots of microservices, they tend to move to Protobuf, Avro, and some other serialization formats that can enforce schema. But then you also need to learn how to properly work with them, because Protobuf and Avro usually have slightly different ways of working with them. Then finally, if you were talking about deploying your HTTP APIs, you also need to think about performance and scaling. Here comes Black Friday soon, so yes, there will be like 5 to 10 times more visitors on the website. Can your model really handle this load? Can it really scale? And what will you do when you updated the model? How your service should respond? Should you redeploy it, or should it do something under the hood and be still available? We just touched a bit performance, scalability, and costs. So we are talking about data science for commercial companies. So we are speaking about profitability. So our solutions should be scalable, and they should consume not too much money. So they should be reasonably cost, right?
Yes, I recently had to improve a large part of code by optimizing the SQL queries and reconfiguring the Spark cluster. I made it run 3 times faster and 9 times cheaper.
I think that's really impressive. But this means there are 2 components in this optimization. So the optimization of the code in this particular case, it's SQL, but it could be your Python code. It could be any other code that really needs optimization, and matching the runtime environment configuration to the job. With Spark, for instance, sometimes it's much more efficient to have less working nodes, but with much higher capacity. Sometimes it actually comes at completely the opposite, the way Spark parallelizes your jobs. Here we have a reference to the things we talked previously. Learn your execution platform. That's the key to all these improvements and controlling the costs. Since we are expected to deliver something that works in production, someone should take care of it in production. And in software engineering, the last few years, it's a common practice with DevOps. DevOps is not a set of tools like CI/CD, it's not a buzzword. DevOps is a culture. Yes, it usually comes together with automation, but first of all, DevOps is a culture. You build it, you run it, you are responsible for it. Again, to fully embrace DevOps culture, you need to think about the code quality, you need to think about monitoring this, but there are lots of tools that actually help you to make at least the first step to delivering scalable solutions, stable, and so on, right?
Yes, versioning is the first thing to do. Start at least with versioning of your code and notebooks. Use Git, of course, even when working alone. The next step are versioning your models and data, because you probably want to compare your new model with the old data and the old model with new data.
Right, or any other combination. These are great tools, and MLflow and Data Lake, any data versioning, they are very specific to data science, while the version source control, testing, and CI/CD, these are common things in all software engineering. And the more data scientists start using those tools, the more effectively they collaborate with each other and with engineers as well. So finally, I would touch a bit of the things regarding system architecture and your data science solution architecture. So no one expects a data scientist to be a system architect, but understanding the very generic things, how the whole solution is built, is crucial, because it gives you insight how you would build your data scientific solution that will be plugged into this whole system, so they act as a whole, right? So you need to know how is your solution is expected to receive data and produce their results. What are the engineering practices in building such kind of things in your organization? What are available runtime environments, and so on and so forth. So that's something you should have at least as an overview. So wrapping it up. So data science and engineering data science, they usually work hand in hand, and together we usually bring value. But the more of engineering know the data scientists, the more effective is this collaboration and the better results we can produce together. So here are those 5 things we think are the most important for a data scientist to learn to become a full stack data scientist. So learn your programming language, learn your execution platform, learn more about the data and APIs, set up the proper workflows, and obviously learn the tools.
Yes, that's all.
Thank you.
Thank you.
Really great presentation, Natalia and Sergei. And we have a couple of questions, but we need to answer it really quick. So we have, do you have any reading recommendation for a full stack data scientist or any other resources?
Nothing that I would immediately come up with. I think this topic, me and Natalia, we are discussing this through the last few years probably. So maybe we should write a book. No, not seriously. But we can think about some other books we could probably recommend, and we will post them later in comments.
Please do. And also I have a question. So how much data engineering and software engineering skills data scientists should have for a junior data scientist and senior data scientist, of course, because these are 2 different levels?
What do you think?
I think the more senior you are, the broader your thinking should be.
Yes, I agree.
So the more senior you become as a data scientist, the more you should know about software engineering. I think it applies not only to software engineering, it applies to everything, because seniority means usually what is in other sources called T-shaped, right?
Yes.
This T center line is your professional things. This horizontal one is the
Soft skills.
and it's not only soft skills, there are hard skills, but in other things like data engineering, software engineering, and understanding the business definitely, and all the other things that all together make you the senior professional.
Really happy to have you with us today, Sergei and Natalia, and really great presentation, and thank you. And for our audience, see you in the next conference.
Oh,
Thank you.
So,
Bye.
bye.
Bye.